So the final talk in this session is on conflict-driven synthesis for web layouts, and is given by Junrui from UC Santa Barbara. On to you.
Hi, everyone. I'm Junrui from UC Santa Barbara, and this is our joint work on synthesizing layout engines with Yanju, Chen, Atkinson, Feng, and Bodik. So what are layout engines? Well, they are pieces of software that takes as input an HTML DOM tree that represents the content of a web page, and also it takes a CSS file that tells the layout engine how to style a web page. And the layout engine is going to compute the visual the visual appearance and also the geometries of the objects in the web page, such as the beautiful PLDI homepage that you see here. So layout engines are very ubiquitous, right? We not only find them in web browsers, but they are also powering GUI frameworks, such as the Electron framework that is behind all of those apps that you may love or hate. And there are some challenges with the layout engines, right? They are very complex pieces of software. For instance, the Blink layout engine, which is used by the Chromium project, has around 4 million lines of code. And also, as you may know, browsers are also used as basis of operating systems. So they're fairly complex. And another challenge with layout engines is that their bugs are layout bugs, which means that they're visual in nature. To the general masses, the layout bugs can make web pages unreadable, but to the visually impaired, layout bugs can make web pages inaccessible. And bugs in layout engines can be very hard to fix because of the mismatch between the intended semantics of the layout features versus the actual algorithm or schedule that that particular feature is being computed. So regarding the last point, here is a GitHub issue from the server layout engine, which is an attempt by the Mozilla team to rewrite the Firefox layout engine in Rust. And in this bug, the developer is quoted as saying, it took them 3 weeks, even before they realized the complexity of the problem. And also the bug is still open until this day. So to address these challenges, we propose to synthesize correct and efficient layout engines. And we instantiate our idea into a tool called Medea. Medea consumes a specification of attribute grammar as input to specify layout correctness. It uses a DSL for expressing layout programs and sketches. And finally, during the synthesis search, it uses a conflict-driven procedure for efficient pruning. I'm going to go into each one of these components in turn. So first, let me start with the attribute grammar for specifying layout correctness. Before doing so, let's consider a very simple example to understand what it means to specify layouts. In this example, we have blocks, which has a width, a height, and a XY coordinates. In addition, let's say our block also has 4 margins, top, bottom, left, and right. And let's call the rectangle enclosed within the margins the content box. The reason we call it content is because we can recursively lay out more children blocks and grandchildren blocks and so on. So this is like intuitively how you specify how to lay out blocks. But there is a well-known formalism known as attribute grammar that precisely specify the layout of blocks. And the attribute grammar has 3 components. First, we must specify what kind of a tree structure is allowed. In this example, we can have a block with any number of children as a list. The second component is the list of attributes that's associated with each node, as you can see on the right. And lastly, there is some relationship between the attributes. For instance, we know that because the child is laid out inside the content box of the parent, we have what's called a computation rule that says the children's width is equal to content.width. As another example, we can compute the width of the content by subtracting from the width of the overall block with the left and right margins as indicated by this computation rule. And you can specify the remaining attribute computation using similar computation rules. So an attribute grammar can formally specify the layout problem, but it's still a declarative specification, so we still need to provide a few more ingredients in order to execute the layout. The first thing is to decide how we are going to perform the tree traversal. Next, we need to come up with a schedule to compute those attributes because the attribute computation rules are an unordered collection of rules. And lastly, here's the fancy animation again. So in case the block is changed by some user input, ideally the layout engine only wants to recompute only a subset of the attributes that are affected. So this is what's called the incremental evaluation. And I have some pretty animation to show that. So if you go to the PLDI homepage and if you click on the attending tab, then you'll see a menu pop up. But notice that the majority of the web page remains the same. That is, due to some user interaction, the layout engine may need to recompute something, but the vast majority of things may remain the same, and the layout engine can skip those computations. Okay, so this is the specification language used by Medea, and now I'm going into the domain-specific language for expressing layout programs and sketches. So as we noted before, there are 3 components that are missing in order to get a functional layout engine. The first is the tree traversal and computation schedule and also incremental evaluation. And on the left, I've shown the context-free grammar of the DSL from Medea. And for now, let's only focus on the first 2 components, tree traversal and computation schedule. So this part of the language is inspired by a previous work. And essentially, this part of the DSL is a functional tree traversal program in static single assignment form. So given a concrete, maybe HTML DOM tree, we're going to run the DSL program, which will evaluate those attributes in turn. And we also have a few high-level constructs for iterating and also for recursively traversing the children. And after the traversal, all of the attributes will be computed by this layout program. However, notice that not all layout programs are correct. For instance, if we move the evaluation of this content.width attribute to the very end of the program, then we're going to run into some problem. The reason is because the attribute children.width has this computation rule. So it depends on the value of content.width. The value of content.width is not computed until all of the children have been recursively traversed. So layout programs have to respect a notion of read-write correctness induced by the attribute grammar, and that is one of the goals for the synthesis. Okay, so now let's focus on the incremental evaluation part of the DSL, which is a main contribution of Medea. So to enable incremental evaluation, Medea takes advantage of what's called dirty bits. So these are inspired by real-world layout engines. So a dirty bit essentially is a Boolean attribute that is associated with one or more attributes that indicate whether that particular attribute has been modified or not by either a direct user interaction, external event, and so on. So we have a set of dirty bits. And to see how dirty bits work, let's imagine that the user has modified the first attribute, and its dirty bit is going to be marked to be true. Now, there are some attributes that depend on the attribute that user just modified, right? So content.x was marked dirty, so this dirtiness will propagate to all the dependent attributes. However, there are also attributes that are not dependent on the things that have been changed. So the the engine can reuse those values because they're still up to date. Okay, so in Medea's DSL, we have this kind of when block to implement the idea of incremental traversal in dirty bits. For example, we can take a non-incremental traversal, as you can see at the center of the screen, and we can simply decorate each attribute evaluation with a when block along with the correct dirty bit condition. However, the notion of incremental evaluation complicates synthesis because incrementality is a spectrum. On the one hand, we can have non-incremental traversal on the left, which will recompute everything every time. On the other end, we also have what are called overly incremental traversals because we are assigning one dirty bit for every possible attribute in the tree, and we have to meticulously maintain the correctness of those dirty bits, which incurs a lot of space and performance cost. But in reality, a lot of the attributes are semantically related, which means that their recomputation can be grouped into blocks. For instance, here is one possible grouping, which groups the horizontal attributes into one group and the vertical attributes into another. So synthesizing efficient incremental traversals requires exploiting the semantic relationships among the attributes while minimizing what are called unnecessary recomputation. So Medea helps explore this vast search space using program synthesis while ensuring correctness. And here is the full synthesis problem. So to use Medea, user provides an attribute grammar specification along with the traversal sketch that only fixes the high-level constructs such as iter and recur, and the user can leave everything else as a whole. Then Medea is going to find a completion of the sketch that has two properties. First, the completion ensures read-write correctness. It doesn't read any value that hasn't been computed, and it also tries to minimize unnecessary recomputation. So, given the synthesis problem, Medea uses a conflict-driven synthesis procedure to do efficient search. And to ensure read-write correctness, Medea uses symbolic execution, and to minimize unnecessary recomputation, Medea uses conflict-driven learning inspired by conflict-driven set solvers. So the high-level architecture is as follows. So given a sketch, we're going to run symbolic execution to obtain a set of constraints to be solved by an off-the-shelf solver, and that gives us a concrete layout engine. But that particular engine might be inefficient for the reason that we just mentioned. So the conflict-driven learning procedure is going to try to infer a set of conflict clauses that prevent the solver from revisiting the same kind of mistakes in future iterations. So this is a iteratively improving the candidate schedule. Because of time constraint, I'm not going to go into the symbolic execution part, but for the conflict-driven learning, I'm going to just give a quick example. So consider this particular incremental block. And suppose that we have two dirty bits, D0 maps to horizontal attributes and D1 maps to vertical attributes. And suppose D1 was marked to be true. Well, this will affect content of Y, which is okay, but we will end up unnecessarily recomputing content of X, but its value is perfectly valid. So there is some unnecessary recomputation here. So in order to improve the schedule, Medea is going to construct a data dependency graph using the attribute grammar and also a few other things. And it's going to identify spurious edges that do not correspond to actual data dependency. And finally, Medea is going to learn a conflict clause, such as one shown in the bottom, to prevent the solver from making the same kind of scheduling decisions. In this case, this clause is saying that in case you assign the attribute content.x into this particular block, then you probably should not assign content.y. Okay, so this is Medea. we have implemented Medea from a specification derived from the CASIA's formalization of web layout. And it supports complex CSS features, including margin collapse, floating layout, and absolute position. And we connected the synthesized layout engine to the Robinson browser engine. And Medea can synthesize correct layouts. For example, we collected 31 real-world layout bugs from Chromium, Firefox, and Safari, and Medea's synthesized layout engine is able to bypass 30 out of 31 of them. The last one being that the feature is not standardized by CSS. And we also experimented with the efficiency of incremental layout from the synthesized engines. So we're going to randomly perturb some kind of attribute on the tree and perform the relayout using the synthesized engines. And we're going to compare 3 candidates, non-incremental, Medea, and also Medea without using any kind of conflict analysis. And we found that Medea is able to achieve up to 4.75 times speedup over the non-incremental version, while if we don't use the conflict analysis, we can only achieve up to 1.73 times speedup. And to explain the difference, we come up with a static cost model that trying to monitor the quality of the candidates as we progress through the iterations. And you can see that Medea generally finds better and better candidates, while without conflict analysis, we're kind of stuck. Okay, so this is Medea, an attribute. It uses attribute grammar for specifying layout correctness. It has a DSL for expressing layout programs and sketches. And finally, it uses conflict-driven synthesis for for efficient synthesis. So this concludes my talk, and I'm happy to take any questions.
Thank you. Questions, please.
Oh, hi, great talk. I'm Kevin from University of Michigan. I have 2 questions. So the first question is, you mentioned in the talk that the children's width depends on the parents. Can you support cases where the parents' width depends on the children's?
That's possible.
Oh, that's possible?
Yep.
Okay, cool. And the second question is, does your layout engine support like more complex layouts like Flexbox, where the children's width has a different proportion with each of them?
No, we currently do not support that feature because it takes a lot of engineering effort to implement the entire spectrum of CSS, but that is something that we definitely want to do in the future.
So your model does support like adding more like difficult like constraints like proportions and directions and stuff? Theoretically, I guess.
I don't think it supports at the moment, but we think that it's possible to encode those features into attribute grammar.
Cool, thank you.
Yeah, no problem.
Hi, Andre Lasker from King's College London. So is the end goal to generate full layout engines or just find bugs and try to fix them with synthesized code?
Okay. So the ultimate goal is to generate layout engines, but that's a very ambitious goal because real-world layout engines are very complex. Even just to connect to the real-world layout engines such as Chromium takes a lot of effort. So right now we're still experimenting with this approach of adding more CSS features to your existing layout engines. But yes, the ultimate goal is to have a fully automated approach to replace the manual effort.
Thank you.
Yeah, no problem.
Hi, I'm Ben from Illinois. Great talk. So given the fact that people tend to want their pages to load extremely quickly, does using synthesis provide any challenges to that? And how do you overcome the scalability issues from using synthesis?
Sorry, I'm not sure I get your question. Can you say that again?
So does the fact that synthesis doesn't tend to scale provide any issues when people want their pages to load extremely quickly in practice? So
the synthesis is done one time. Like we construct one single layout engine that is run whenever you want to load a page. So the cost of synthesis doesn't happen during runtime. Is that your question?
Yeah, thank you.
Okay, great.
Hi, thanks for the great talk. I was curious, it seems like this really helps with, say, the complicated specification of something like CSS and trying to nail that down. It seems like your last example of a bug in the specification was very much that point. But your earlier example of the GitHub bug looked like it was more about the numerics involved. I'm curious if you have any sense, which I know is a substantial issue for actual layout engines and a cause of discrepancy between browsers. Was that an issue you all saw or ran into? Do you feel like this is orthogonal to those concerns? Do you have any comments on that?
Sorry, I am lost. When you say the GitHub issue was?
It looked like it was about the numerics being used. The one you said took like 3 weeks for them to understand what was going on. It seemed like it wasn't about the orchestration of different layout rules, but perhaps about numerics from the image you had on your slide.
Oh, so that particular bug was more of due to a architectural decision made by the developer. So they have two features that actually interact, but they implement that as separate phases. So fixing that bug requiring distributing those two features across each other. And I believe using our tool, we can get rid of this bug by using synthesis.
I guess maybe even if that wasn't quite the thing, I know that numerics are sometimes an issue for consistency across layout engines. Do you feel like that's a non-issue? Is that an issue being addressed by this synthesis approach, or is that something that's mainly orthogonal? That's sort of the nature of the question.
I see. So you're saying about different layout engines have different behaviors? Is that your question? And is that important?
Yeah, because of how you handle coordinates. So if you use floating point or fixed point of different degrees, or this is non-associative, or it is.
Oh, I see.
Like
so,
this was a whole scheme for fingerprinting browsers, for instance, was just the fact that things would end up a pixel off, or this could like break layouts as you move between different browsers. And
okay.
I can talk with you about it after.
Okay, yeah, it's definitely interesting.
Thanks,
Yeah,
appreciate
no problem.
it.
Thank you.
Well, okay, so that concludes the session. Let's thank Junrui again.